Okay, I hope that Chapter 8 went well for you all. Let's just dive right into Chapter 9, which partners with Chapter 8, because Chapter 8 talks about Lewis dot structures and how those electrons arrange themselves around a central atom when it's bonded together with other atoms covalently. And then Chapter 9 talks about how those atoms, or those electrons around those atoms, interact with each other and help the molecular geometry, the shape of the molecule itself in space. So they do go together, and it's actually quite interesting, and it has a lot to do with our everyday life and how those molecules interact with each other. In the case of water, for example, the molecular geometry gives water its very unique properties, and that our lives depend on it, literally. So let's talk about what we're going to discuss in Chapter 9, the Vesper model, which governs how that geometry is determined. We're going to talk about what is a domain. We're going to talk about how does it deviate, although we're not going to talk about it too much because I don't want you to get too bogged down in those kinds of things, not at this level anyway. And then what if there's more than one central atom? Now, we did discuss what is a central atom a little bit last time. When you have atoms bonded together, you have to have something in the center, and that central atom is called the central atom. And that's what we're going to talk about. Let's talk about first, what does Vesper mean? Vesper, the word, or an acronym Vesper, stands for the valence, it's right here, valence shell electron pair repulsion model. That's what it stands for. Valence shell, so that's your outside energy level, electron pair repulsion. Because keep in mind, please, that electrons, especially when they're not bonded, but electrons are negatively charged, so they really do not like, this is Vesper right here, here's the V, valence shell electron pair repulsion, Vesper. They don't like each other, electrons, so they're going to pull apart, repel each other in a molecule. And especially if they're alone, if they're a lone pair, they're going to push away far. And you learned about this, a lot of you that did your molecular geometry lab, you saw this. They had the little flat shape in your kit, so you could see this and how it affects the shape of the geometry of the molecule. So in here it talks about many familiar chemical and biochemical processes totally depend on these 3D shapes of the molecules. In Chem 2 just the other day, we talked about whether or not reactions are going to happen, and it totally depends on how they're facing each other, and if those, when they slam into each other in space, are they even turned the same way? And the complexity of the molecule itself helps to determine that. So it does play a part, actually an important part, and the Vesper model has a lot to do with that. So let's talk about this. And the total basis of this has everything to do with those electrons, especially the unpaired electrons, the ones that are not being shared between atoms, those lone pairs of electrons. So we're going to learn a new word today, and that is domain. And when we're talking about a domain, let's talk about this central atom, okay? And for this purpose, we're going to talk about the central atom and the electrons that are around that atom in terms of whether they have bonded electrons or whether they're unshared. So an electron domain is how many pairs of electrons, paired electrons, does it have around it. Okay, now that means whether they're alone an unshared pair or whether they're bonded to something else. Okay, whether that bond is a single, double, or triple bond. If they're bonded to something else, that's one single domain. If it's an unshared pair, that is another domain. So we're going to see what that means. Let's watch and see what that means. Here's a good example here's carbon dioxide, for example. Carbon dioxide has carbon as its central atom. Carbon will always be the central atom when it's bonded with other things. So here's carbon. Notice it's got oxygen on either side of it. So these two oxygens are called, remember, the terminal atoms in this case. So we have carbon in the center, and notice please that you have it double bonded on this side and you have another double bond on this side. So you have in total 8 electrons involved in this. Four electrons are shared over here, or 4 pairs rather, and 4 on this side. So that's a total of 8 electrons altogether. Okay? However, there are only 2 domains, because even though this is a double bond and this is a double bond, it's tied together one time on each side. So that's 1 domain on each side for a total of 2 domains. Let's talk about ozone. We talked about ozone in Chapter 8. Here you have a domain right here, 1 tied up space here, 1 tied up space here, and then 1 unshared pair up top. Okay, so that's a total of 3 domains around that central oxygen. Here our central atom is nitrogen. You have a pair that's shared here, so that's tied up. You have a pair that's shared here, that's tied up. You have a pair that's shared here, that forms a domain. And then you have this unshared pair here, and that forms a 4th domain. So you have a total of 4 domains in this situation. Okay, so let's find out what that means. In your textbook, it on page 366, it shows this, and those electron domain determines the overall shape. Okay, the Vesper model predicts that these electron domains, they're going to repel each other, so they're going to arrange each other so that they're as absolutely far apart as they can possibly get. So in the case of these first 2, this it's going to be more linear. It is going to for sure be linear in carbon dioxide. As far away from they can get from each other in this first one is straight across. All right, that's as far away from each other as they can possibly get. All right, they used balloons on page 367 to sort of show you what they're going to look like, and the fact that those lone pairs really push things down will let you see why the ozone in this middle one here is not going to be completely linear. Let's look and see what I'm talking about. Here, there's nothing to keep this carbon dioxide from being completely linear flat. Okay, this one here. However, this lone pair of electrons right there can push this down. Now, it cannot do anything to this double bond because it's very strong, but it can push this oxygen down. So this ozone is bent a little bit. Okay, you'd think it would be linear, but it's not, because this unshared pair of electrons right here can bend this down. And the same is true. Even though this looks like it would be the shape right here drawn, this unshared pair of electrons right here pushes everything down. So the actual shape is, here's our nitrogen, here's our unshared pair, and it actually gets pushed down so it looks more like a pyramid or a tripod. And that's what the Vesper model says, that those electrons are going to repel each other and push things down and lend itself to the three-dimensional shape. That's called trigonal pyramidal. So if you have an unshared pair of electrons. And on page 369 in your text, it really shows a good picture of what's going on in this situation and what you can expect, what domains are talking about, and what where the lone pairs are and what those lone pairs do and how they push things down and make them look different than you would perhaps expect them to look. So, and it gives you examples as well. It gives you, if you have one lone pair, notice that it's going to make it bend. It's going to push those down. If you have two lone pairs of electrons, it's really going to push it and make that angle even more pronounced. So on page 369 of your text, it's going to give you these examples. Also, on the top of 368, you're going to see some bond angles. And when we're talking about bond angles, there's two different bond angles that we can be talking about. It can be talking about, let's talk about this case of this ammonia right here, this NH3. We could talk about the bond angle between the two hydrogens here, or we could talk about the bond angle between the nitrogen and the hydrogen here. So there's two different ones that we could be talking about, and so it's going to stress to you which one it's talking about, and you're going to have to pay attention to that. All right, let's look at the sample problem. Let me undo my pen. Here it's showing you with these balloon models how these electrons are going to push away from each other and modeling the Vesper theory and how they're going to push away. Those electrons are going to push away, repel unshared pairs of electrons, a pair that's unshared between another. And this is what I was telling you about, the bond angles that are on page 368. And you could talk about the bond angles between, so a linear, 120 degrees, 180 is a flat line. Okay, you need to be familiar with those. I put some of those on your homework quiz. And then this is where we also talked about on page 369. Okay, I believe I explained this to you, I hope, fairly thoroughly from the text. And this is also in your textbook on page 369, I believe it is. Yeah. Notice what happens. You have the electronic domains that are listed there. And so that means that you have 3 atoms involved. Maybe 2 are the same. And then how many lone pairs, though, do you have of electrons? And that's going to push your atom. All right, and that, again, that's on page 369. You have that chart. But I wanted to work a practice problem with you guys. Okay? Considering these summaries. We're going to work this practice problem, but in doing so, let's consider this summary. Okay? First, you're going to draw the Lewis structure. Then you're going to, how many domains are there? You're going to count those domains. Keep in mind what a domain is. It is how many bonds are there. It doesn't matter if that bond is single or double or triple, if it's bonded between two atoms. How many places is it tied up to another atom? And then the central atom is what we're talking about. Keep in mind that. And then how many unshared pairs does it have? So that's how many domains it has. Okay, any bonds plus any shared pairs, unshared pairs. That is a domain. Then you're going to consider that chart that's on page 369 and what the Vesper model, this is a breakdown of what the Vesper model says based on that applying, how much are those electrons going to repel each other. And then that, what is the geometry, the overall geometry of the molecule going to be? Okay, what is the electrons spread out going to be? But then what is the overall geometry of the molecule going to be based on how are those electrons that are unpaired going to push the molecule into a 3D shape? That's what you have to consider. Okay? So here it's asking you to determine the shapes of these two molecules. You have sulfur trioxide, and you have this polyatomic ion here. Here you have an ion that's got one iodine and 4 chloride ions in it. So these two shapes. Now please let's talk about how many electron domains we have in the sulfur trioxide. In the sulfur trioxide you have 3 bonds. One of them is a double and 2 single bonds around your central atom, and no unshared pairs of electrons at all. So you have 3 domains. 3 domains. All right? Well, if you turn back to page 369, what does that mean? What does that overall shape going to be then? If you have an AB3, what does it mean if you have an AB3 and no unshared pairs? What is that going to look like? Okay? And then what about the polyatomic ion? Notice how many domains you have on that one. You have 4 single bonds, plus you have 2 unshared pairs, because iodine is can expand the octet rule. So look at what you have on that one. In that case, you have AB4, and you have 2 lone pairs of electrons. So you can see what shape that one's going to be overall as well. Let's flip to the next page, and you can see that because from page 369 you have that AB3, that electron shape is going to be trigonal planar. Okay? It's going to, because it doesn't have any unshared pairs. It's and then the other one is going to be square planar, like at the bottom of very, very bottom of page 369, that AB4, because it has 2 unshared pairs of electrons, and it's really going to push everything away, even though it looks like it should be octahedral because it has those 6 domains. The fact that 2 of those are unpaired makes it flat like that. Okay, So that's super important that you get that. All right. And that was on pages 369 and 370 of how you'd work that out. All right. Okay. And then remember, if you have some deviations from ideal bond angles, notice this, that a lone pair is going to take up more space. They're going to take up extra space simply because they're going to get as far away from each other as they possibly can. Okay? And they have more density. They're single, after all. So they are going to take up more space. And then also, if you have double, triple bonds, they're going to be able to repel even more strongly than single bonds. So they're going to be more repulsive than single bonds are going to be. So they can really affect that geometry of the molecule even more so than a single bond can. So that's going to bend the molecule even more, and it's going to affect the bond angle more definitely. It's going to have a stronger effect on the bond angle than a single bond would. What about in the case of something like this that has, this is methanol, methyl alcohol like they use in airplanes for fuel. What about in this case when you have not just one central angle, but two? When you have two central angles, now carbon is your main central angle in this case, but oxygen's more electronegative. So what if you have this, you're going to consider each one separate, okay? And then you're going to talk about which one's going to behave more ideally, okay, when that occurs, all right? And so that's what you're going to do. Here's another one. You got two different carbons. So you're going to consider each one individually, and then you're going to consider the whole of it is what you would do. And this is where your model molecules are really going to come in handy, because they are geared in such a way, especially the black carbon molecules, so that they can help you to see, and be sure that you use the bendy ones for double angles and triple angles, and the little short straight ones for single angles. Okay? All right. And then we get into molecular geometry and how is that affected by polarity. Please keep in mind things like oxygen, fluorine, chlorine, those are your most electronegative on the chart, and they're going to greatly affect the geometry, the overall shape of a molecule. Remember the symbol for polarity is that kind of funny looking cross thing with the arrow, and the arrow is going to be pointing towards the most electronegative. All right, and to find the overall polarity, then you're going to sum them all up. That sigma, that funny looking, most of you probably already know this, but this funny looking E-looking thing is a sigma, which means add them all up, sum them up. It stands for the sum in math. So you would have to say, okay, add it up in this direction, add it up in this direction, and then add those two things together to get the overall sum. And when you have molecules that can have more than one chemical formula, but they can be arranged in different directions, they're called structural isomers. Same formula, like perhaps you have C, in this case, you have C2, looks like H2O2. And you have two different ways that can be arranged. You have the top one and the bottom one. And this is cis and trans. And so if you have these two options, then you have to add up how many are the trans and how many are the cis isomer. This is more of a Chem 2 question, though. But cis means that the different element, in this case the oxygen, are on opposite sides. And the did I say cis or did I say trans? The cis means the same. So cis would be same. So this molecule down on the bottom right here is cis because our two oxygens are on the same side. And the trans is on the opposite sides. So that top one there is trans because the two oxygen atoms are on opposite sides. That's what, but they're still called. So this one's trans right here. Opposite sides. Cis, same side. And they're called structural isomers. They're the same in every single way except for how they are oriented, how they're put together around their central atom. Now, can these spin and become the same? Yes. But what if there was a double bond in there? If there was a double bond, they'd be stuck like they are. Okay. All right. Now, we're going to learn how to put these together, but I think that that's enough for right this minute.